Okay, so we left off last time talking about rejection sampling and adaptive rejection sampling. And in the bigger picture, we were talking about what happens if you have a distribution that you want to sample from, and then you don't have a tractable way of actually sampling directly from that distribution. So the name of the game in rejection sampling and adaptive rejection sampling is to find some an enveloping function, an enveloping density that you can actually sample from easily. Sample from that and then reject the ones that don't satisfy the conditions such that you set up the conditions such that once you do the rejection, you're actually sampling from the density of interest. The next thing we're going to talk about in a second is importance sampling, where instead of accepting or rejecting as a 0-1 decision, you basically reweight the samples that you get. So you're still going to choose some other density from which to sample, but then you're going to take the samples that you get and reweight them such that they have the property as if they were sampled from the density of interest. So that's sort of the general story. I forgot when I was talking about rejection sampling that I had sort of a nice little example of doing rejection sampling. So I'm going to go through that a little bit. So one example with rejection sampling is, suppose you want to sample from a truncated normal. So if you were trying to do that, so I have some normal distribution, and suppose I want to sample somewhat far out into the tail. Well, I could just sample from the normal distribution and reject everything that is on this side of the censoring point. But the result of that is I'm going to spend all of my computation essentially sampling points out here that I then subsequently throw away. So that seems a little bit silly. You can actually use inverse CDF for this, which isn't bad, except that if you get far enough out in the tail, you can have some numerical issues with that. And so rejection sampling is another thing that you can do. And the basic idea is, if we think about this tail here, part of the reason I'm going through this example is just because these questions about thinking about tails come up a lot. If we think about this tail, this is decaying exponentially as the square of the value of x. Well, now if we think about an enveloping function, we can think about the fact, well, if I had some sort of exponentially decaying tail that just decayed as a function of x instead of x squared, then I would be able to use that as an enveloping function. Okay. So I could actually use an exponential density or distribution as my sampling density for the tail of a Gaussian distribution. And that's just because the exponential distribution has a tail that's going down more slowly than does the Gaussian distribution. So I need, the usual exponential that we think of is, okay, it looks something like this, where this is 0. So what I need to do is basically take this density and shift it out here and scale it, with my constant c to make sure that it's above the tail of my normal distribution for the entire part of the distribution that we're looking at. So that's the basic idea there. And there are some details here in terms of me setting up this shifted exponential distribution and calculating c. And there's a reference in the notes to the paper where I got those details from. So I won't go through the details of exactly those calculations, but the idea is, suppose we want to sample from a normal distribution with mean 1 and variance 4, and sample from it such that we're only sampling values bigger than 4 in that distribution. So if I do that just by sampling from the standard normal distribution and then rejecting those that are less than 4, indeed I'll get the sample from the distribution, but I also see that I only am accepting about 7% of the samples, so I'm wasting all the calculations for 93% of the samples. Okay, so here are the sort of details that I'm gliding over in terms of setting up the exponential distribution. This actually samples from that shifted and scaled exponential distribution. Okay. And then we have to sample our uniform values and do the acceptance rejection. So that's what this step does. And what we see when we do the sampling from the exponential distribution is that we get an acceptance rate of about 91%. So that says we're wasting much less of our calculations when we do it this way, as opposed to doing it the initial way of just sampling from the normal and throwing away everything in the tail. And the main thing I wanted to show was just to sort of show you some plots of this and just see we can get a little bit more of an intuitive sense of this. So the red ones basically are the ones that are accepted, and the black ones are the ones that are rejected. So basically, we're sampling from something that looks like, well, let's see, what am I doing here? This is basically on the scale of that uniform random variable that I had to draw to decide whether or not I was above the density or below the density relative to the envelope. And you can see that I'm accepting most of them. But once I get further out in the tail, I'm actually rejecting most of them. And that's because the normal distribution tail is decaying so quickly relative to the exponential tail that basically I'm always above, when I sample out there in the exponential density, I'm always above the density, the normal density tail of interest. So all of these, so most of the ones out here are rejected, but luckily, because the exponential density is also decaying quickly, I don't actually sample very many from the exponential density out here to even start with. And so as a result, most of the values that I sample are accepted. And I can also add a plot here that's going to show the red is my density of interest, that's the normal density, and then the black is the exponential scaled up so that it's always above the normal density. So you can see that there's not all that much of a gap. And on an absolute scale, there's not that much of a gap between the two tails down here, but on a relative scale, this is actually a huge difference between the exponential tail and the normal density tail. And we could sort of blow that up and look more closely out in the tail. And this is again on an absolute scale, but this is just looking at values very far out in the tail. We can see that the exponential density is quite a bit larger than the tail of the Gaussian distribution. Okay, so any questions about that? Okay, so the last thing I wanted to talk about in the simulation unit was this notion of importance sampling. So the basic story here is, suppose that importance sampling is mainly focused on estimating expectations, so means and variances, third moments, things like that. But you can basically do it for any function h of x. So this could be x. This could just be x, in which case this is the expected value. This could be x squared, in which case it's the variance, or closely related to the variance. But any other functional of interest we could also do here. So this is taking the expected value for h of x when x is drawn from some distribution f. So the trick here is not to draw from the f itself, the idea again being that it might be a hard distribution to sample from. But we're going to do a trick. We're just going to multiply and divide by some g. So this is going to be some other density that we're going to use. And the idea, again, sort of like rejection sampling, is we want to choose a g that's easy to sample from. And then we're going to do a correction for the fact that we're sampling from g instead of sampling from the f that's the thing of interest. So I've written in sort of an evocative, hopefully evocative way here, which is if I look at this, I've written it such that if I just sort of cover up this for the moment, I say, well, this is some expectation with respect to g. So all I need to do is just sample from g and then take a Monte Carlo average of the values of h times f over g for each of the x's that I sample from g instead of from f. So going back to our idea of Monte Carlo estimation, our estimate of this expectation is going to be the average over m different samples of x, where I take m samples of x from g, and then I take this average instead of just taking the average of h, which is what we saw at the beginning of the section, at the beginning of the unit. So what is this? Well, this is basically just a weighted sample. Right? So usually we're just taking the Monte Carlo average to be this. Now we're introducing these weights that are f over g, so I can just write, that I'm going to call these things wi star, and those are just the weights that I use. So basically what I'm doing is, in order to get the sample to be representative of the distribution that I wanted to sample from, I'm going to find those. I'm basically finding whether or not, if I have a case where f is much larger than g, that's going to have a big weight, because in that case, those are the values that I'm not sampling enough from g. G is underrepresenting f with respect to values like that. So I need to upweight those guys. And in the cases where f is much smaller than g, I'm going to get many more of those sampled from g than I should have if I were sampling from f, so I need to downweight those guys. So we're just sort of adjusting on the fly to to what's gone on in terms of sampling from G instead of sampling from F. Okay, so one of the nice things about importance sampling, unlike what we saw with rejection sampling, is I don't have to have the distribution that I'm sampling from be above, or a scaled version of it, be above the distribution of interest all the time. So that makes it easier. But some of the same considerations about whether the tail is heavier in the sampling distribution or in the distribution of interest still come into play here. And that's actually what you're going to explore in more detail in one of the problems on the problem set that I just posted today. So the idea is the densities just have to have common support, so I have to be able to draw samples from everywhere in the domain of F, but I have to be able to draw from, G has to be able to give values anywhere that F can give values. But the problem arises when G, the density I'm sampling from, has a lighter tail than the density that I'm interested in. Okay, so the idea is that's sort of the main thing that's sort of the main issue that comes up in importance sampling. So the idea here is let's talk about that for a little bit more. So suppose I have some distribution. I'm going to draw the tail sort of thicker here. So this is this thing that I would like to sample from. But instead, suppose I sample from something that doesn't quite look like this, and it has a much lighter tail. So what's going to happen? I'm going to be sampling from this thing. Every so often, I'm going to get a value that's out here in the tail. Not very likely, because that tail, I've already said, is kind of a small, a lightweight tail. But every so often, I'll get a value that's sampled from G that's out in the tail. And suppose that this is many, many orders of magnitude, or suppose this is orders of magnitude larger a value when I take f of x relative to when I take g of x. So I've got f of x much bigger than g of x. Well, we can think about what's happening sort of intuitively here is I'm not getting enough values out in the tail when I sample from G, so I need to upweight that value to reweight the relative distributions. But the problem is I don't get very many of these to upweight. So suppose I only get one or two of these out here, and they have a huge weight because I need to upweight when I'm out in that tail. So I don't get very many of these, but I need to upweight them a lot. And so the result is that I get a few of these weights that are really, really large. So I'm now taking a weighted average where many of these weights are pretty small, and just one or two or a few of these weights are really, really big. So you can imagine that that would not be a very reliable or robust estimate of this expectation, because I'm relying so much on just the pure chance of what particular value, or one or two or three values did I happen to draw out here, and how far out here were they? They're not very representative. And we can think about that in a little, that was sort of more of a sort of hand-wavy kind of argument, but we can also think about, well, what is the variance of my Monte Carlo estimator? So recall this, we talked about the idea of the simulation error in the Monte Carlo estimator a couple of classes ago. Well, that's just this. It's the variance of the thing that is usually of h of x, but now of the weighted version of h of x. And this variance is going to be large. If I think about the individual values here, they're going to be, if I've got some that have very large weight, where I'm going to have a few of these that are much bigger than the other ones, and that's going to be a high variance. The result of that is that that's consistent with having a high variance Monte Carlo estimator. So that's sort of main thing that we want to avoid is in this situation of having our sampling density, the G, have much lighter tails than the density that we're interested, the density that we would like to sample from. Okay, the other thing I'll mention here is sort of a cool thing that has some sort of statistical connections, which is we can think about what we want G to look like in another sense of reducing the variance of our estimator. So I'll do this sort of by way of an example. Suppose I wanted to estimate the probability that the probability of x being less than some value when x is drawn from f. So suppose I've got some distribution f, and I'm interested in the expectation of the indicator of x less than some constant c. Well, this is just the probability that x is less than c under the distribution f. Okay, so suppose that c is here. And now suppose I'm thinking of using importance sampling to do this, to draw from, to calculate this, estimate this expectation, which is its probability. So I could think about choosing some g that sort of tries to match what f is, but I can actually be somewhat smarter than that, because what's happening with h? Well, the h function is basically just this function here, right? It's just an indicator function that's 0 here and 1 when I'm beyond there. Okay? So the smart thing to do in this case is actually to have g, my sampling density, put a lot of its mass out here and not so much of it here. Okay? So I might choose a g that looks sort of like this, for example. And then the question was, well, why is this a good thing to do in terms of reducing the variance of my Monte Carlo estimator of this expectation, such that maybe I can draw fewer samples than I otherwise would have to? Well, the basic idea comes down to, again, this idea of this variance. And the idea is if I want to have this, if I want to have these values be small and similar to each other, such that the variance is small, then what should I do? Well, where h is big, bigger than in other places for the values of h, I want to have g be big to sort of cancel it out. Okay? Well, what does that mean in terms of the picture? Where h is bigger than it is otherwise, I want to have g be big relative to f, such that I sort of cancel out the h. And so that's going to give me a lower variance estimator if g is big where h is big, and f is big where h is small. Okay, so that's basically the picture that I've drawn here. Okay, so another couple ways to think about this is, what am I doing? I'm concentrating all of my sampling power, or maybe power is a bad word to use, but I'm concentrating all of my sampling effort on the places where h is non-negligible. So that sort of makes sense. I want to sample in a biased fashion such that I'm sampling where h is actually has most of its mass. And I think that sort of idea of oversampling is sort of something that you would see in survey sampling and things like that as a way to reduce variance in estimating things as well. So that's hopefully helps to give a little bit of intuition for this. Another way of thinking about it is, what's happening when I sample from f? Well, I'd sort of like to be, I'm not putting a lot of samples out here. I'd like to sort of sample more from out in the tail, because that's where all the action is in terms of h. And so that's what this importance sampling estimator does. Okay, so any questions about that? Yeah, Tom.
So in this method, you still have to calculate f, right?
Yeah, you still need to calculate f. So there's the sort of general story in a lot of these methods is we can evaluate the function f, but we don't have a good method for sampling randomly from that distribution. Well, you need I give you some arbitrary f, right? There's unless you have an algorithm by which to sample from it, you need to come up with some numerical recipe for actually drawing values from the distribution such that the values satisfy the probability distribution. So you can inverse CDF is one way to do that if you can invert the density, invert the CDF. If you can calculate the CDF and then invert it, but you can't always do that. And particularly that's going to be harder as you get into higher dimensions. So often we end up only being able to sample from certain tractable distributions, and then we need to use tricks to sort of correct things or adjust things so that we're actually sampling from the distribution of interest. Okay, other questions? So the last thing I'll say about this is I had said sort of explicitly the main idea of importance sampling is to estimate expectations as opposed to drawing random samples that are then representative of the distribution of interest from which you could then do whatever you want. But we could use importance sampling to actually draw a sample, and the basic idea is we're going to draw x and then we're going to get these weights, and then we're going to resample from x according to the weights, and that will do the same. That will do a correction to give us a sample that's representative of the actual distribution of interest. Okay, so I think I'll basically close off there in terms of the simulation unit. There's this method called ratio of uniforms that I put in here a couple years ago, and I've sort of forgotten when this is really helpful. So I'm gonna skip over that. If you come across it, you could come back to these notes, and maybe they would be helpful. And then we've talked about simulation studies in sections, so I'm gonna skip over this as well. Okay, so we're gonna next start in on optimization. So let's see, where am I here? Okay, so give you an idea of the plan for the rest of the semester. We're going to spend maybe 5 or 6 days on optimization, so basically next week and the week of Thanksgiving. And then the last week of classes, which is the week after Thanksgiving, I'll probably spend a day or two talking about numerical integration and numerical differentiation, and then maybe a day or so talking about graphics in R and sort of good principles in terms of graphics. So that's the plan. I have a couple references here in terms of the optimization. Okay, so actually before I jump into this, just to get a sense of where people are coming from, how many of you are reasonably familiar with Newton's method or Newton-Rapson? Okay, so a reasonably large number of you. So we're going to see Newton-Rapson both in one dimension and in higher dimensions, and we're going to see a variety of other optimization methods. I know some of you are from industrial engineering and operations research, and you guys, I think, probably see optimization quite a bit. So please do jump in if you have any thoughts as we're going along here. Okay, so when we're doing optimization, we're often going to be making use of derivative information. So we're going to be either hill climbing or seeking a valley, and we're going to try and use derivatives to get us to the peak or the valley more quickly. So just in terms of notation, the basic idea is we're going to be trying to optimize some function f with respect to arguments x. And x might be a scalar or x might be a vector, so we might be optimizing in a p-dimensional space. And if we take all of the individual first derivatives and collect them, that's going to give us the gradient vector, which I'll either use f prime or this gradient notation. And if I collect all of the second partial derivatives, I'm going to denote that as either f double prime or this notation, which probably has a name that I'm forgetting. This is also called the Hessian, which you'll also hear me refer to. And that's basically this matrix here. Okay, so the notation can get a little bit annoying sometimes, and actually it's already not all that great here that I'm using subscripts in different ways here. So here I just said x can be a vector, and now as we're doing our optimization, we basically have to start somewhere, and then we're going to take moves to try and search our way through the space and try and find the minimum. Usually we'll frame the optimization as a minimization. If we're actually trying to optimize, which we would be doing with the log likely, we could just take the negative of the function, and that's going to give us a problem that we can then minimize. So the basic idea is I'm going to start somewhere, so that's going to be x sub 0, and I'm sort of searching in this space. I don't know where the minimum is, but suppose it's somewhere over there. Well, I'm going to take a step that I hope is in the right direction. That's going to get me to x1. Now I'm going to sort of look around, try and use the information I have at this particular place, and hopefully take another step that leads me closer to the minimum, and then keep walking my way through the space. So I'm going to denote that as x0, x1, xt plus 1, where t is time or sort of iteration time, so as I'm searching through the space. And the optimum is going to be at x star. That's where we're trying to get to. Okay, so any questions about the notation? Okay, so often I'm going to use x sort of more in an optimization context, but if we were working in a statistical context where I was trying to maximize a likelihood, we might be using notation like theta, where theta is the vector of parameters, and I'm trying to find a maximum likelihood estimate. So I'd be trying to maximize some function as a function of theta. Okay, so the idea is in many statistical problems we can't do the maximization analytically, so we have to come up with a numerical algorithm that's going to lead us to the optimum by taking steps in particular directions. So some of the things that we might be trying to do is find a maximum likelihood estimator for a generalized linear model. If we have a nonlinear regression model, we might be trying to find an estimator find the best parameter estimates for that. We might have a likelihood that we're trying to estimate under constraints, so there might be problems where we've got constraints built in, and we'll talk some about constrained optimization as well. Okay. So let's start talking about methods for doing this. And we're going to start in one dimension, and the reason is that often we're not working with a function that's just a function of a single scalar argument. But it helps to get us some intuition for this idea of sort of searching through the space. And when we're doing multivariate optimization, often those methods are just going to be extensions of what we see in one dimension. So we might, for example, be following a recipe where we're starting in some place, we're trying to find the minimum. We come up with a way to choose a direction, and then we might try and find the best value, the optimum in that direction. So the minimum if we're only traveling in this direction. So we'll do a one-dimensional search, try and find the minimum in this direction. We'll stop at the point where we find the minimum. Now we'll look around and try and find the next direction that we want to go and try and find the minimum in that direction. So sometimes these things can be reduced down to one-dimensional operations within a multivariate optimization. Okay, so some of this is now going to sort of go back to basic calculus and working with derivatives and what does it mean to have first and second derivatives. So suppose I've got some function that I'm trying to minimize. Well, I know that the minimum is going to occur where the derivative is equal to 0. And I know that that will either be the minimum or it might be a maximum. And if I want to distinguish between the two, then I can look at the second derivative to tell me whether it's a minimum or a maximum. So you guys have all seen this in calculus. So just to sort of fix our intuition, okay, so here we've got a place where the gradient is 0. And if we think about the second derivative, which is basically the change in the gradient, well, the gradient here is negative, the gradient here is 0, the gradient here is positive. The second derivative is increasing throughout this function because the derivative is going from being negative to 0 to positive, and that means the second derivative is the gradient of the gradient. The second derivative is positive everywhere here. The second derivative is positive here as well. Okay. And if we're in multiple dimensions, what we need for this thing to know that we found a minimum as opposed to a maximum or a saddle point where we're finding a minimum and a maximum at the same time in different directions, is that matrix of second partial derivatives is positive semi-definite. So we're sort of coming back to some of the ideas we saw in linear algebra, that some of these ideas come up here in optimization as well. Okay, and I'm going to concentrate on the case where we're optimizing over a continuous x as opposed to a discrete x, although sometimes optimization comes up in discrete cases as well in statistical contexts. Okay. So the basic idea for the unit is we want to understand one-dimensional line searches. We want to have some understanding of multivariate methods that do optimization in higher dimensional spaces, either with gradient and derivative information or without using it. And some I get some sense for how to do some of these operations in R. And then I'll also talk some to give you a little bit of an idea of what convex optimization is all about. Okay, so let's start with univariate optimization, and we're going to start with something called the golden section search. Okay, so the idea is we have some function, and we don't know where the minimum is, but we want to find it. So suppose maybe the function looks like this, and we know that the minimum lies in some interval, and we know there's a single minimum in that interval. So the question is, how do we go about finding this interval? Well, sort of a really slow, sort of in relative terms, a slow way to do this would basically be to sort of divide up the interval into many, many values, exhaustively evaluate what the value of the function is for all of those, basically find out which 2 points basically surround the minimum, and then suppose those 2 points are here, then do another grid search in here and basically narrow down until we get close enough that we say, well, it's close enough for our purposes in terms of having found the minimum. So if we do it this sort of exhaustive way, that's going to take a lot more computation than we actually need to do. So the idea is to be smarter about doing the computation. On the other hand, if the function were not unimodal, if there wasn't just one minimum, then we might actually have to do this more exhaustive search. Suppose the function looked like this. That's going to be something that's hard to that's going to be something that's hard to minimize without doing something where we're doing a lot of computation, because there are all of these local minima in addition to the global minimum. Okay, but for the golden section search, we're going to assume we have an interval, and we know that the function is unimodal in that interval. So there's a single minimum. Okay, so what's the idea of doing the golden section search? Well, the idea is we're going to choose two values, and for the sake of starting this off, let's just suppose that those two values are splitting this area up in thirds. Well, what do? Well, we basically evaluate the function at all four of these points. And then we basically are going to try and rule out the minimum being here or here. So the basic recipe is that, where do I have it here? So we want to see is f of x1 less than f of x2. So this one is x1, this one is x2. We know this thing is unimodal, so if this guy is lower than this guy, once we evaluate f of x1 and f of x2, then I know that my minimum has to be in this interval here, and I've ruled out this part of the space. And if I find out that the situation were reversed and it were like this, well, then I've ruled out this part of the space, and I can concentrate on my efforts in this part of the space. So the question of how to divide this up in where to choose x1 and x2 comes down to try and figure out how to do this in an efficient way. So since this is going to be an iterative algorithm, so suppose I've gotten to this point and I've realized that, okay, the minimum must be somewhere in here. Now I'm going to choose another point at which to evaluate. So suppose I choose this point here as x3, and now I'm going to repeat the process. I know what the value is here, 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 and here. Actually, I guess I don't even need to know the values at the boundaries. And now, for example, suppose I find out what the value is of x3. Well, now I can think about x2 versus x3, and now I know that my minimum is going to be in this interval. But the thing you'll have noticed when I've just done this is now at this second stage, all I've done is I've ruled out this piece, and I've sort of kept the majority of I've kept a sort of large majority of the interval that I was working in. So I sort of got unlucky, and I was sort of inefficient about the fact that I'm only ruling out a relatively small piece of this entire interval here. So the idea of the golden section is to come up with a rule that tells us exactly where to place x1 and x2, such that at every iteration I'm removing the same proportion of the remaining space as I'm doing my search. And that's going to be the most efficient thing to do. So the question is how to do that, is how to actually do that. And the idea is as follows. So the idea is I have my interval. Suppose I call that A, B. And I'm going to think about dividing the interval up like this. So I'm going to have equal amounts here and here. Let's call that 1 minus phi. I'm going to say this whole thing has relative length of 1. And if I do that, then what remains in the middle is going to be 2 phi minus 1. Okay. So I know I'm either going to eliminate this piece or this piece at the first stage of going through the iteration. So I'm going to be left with just this. And if I do that, and I now place my new point, if I now place a new point such that these two are equal to each other, then this is going to be 2 phi minus 1. This is going to be 2 phi minus 1 as well. This whole thing here is still 1 minus phi. And the idea is to choose, so at this point I've eliminated 1 minus phi out of the total length of 1. And if I want to eliminate the same proportion at every stage of the iterative algorithm, at this point, I'm going to eliminate either this or this. So I'm going to be eliminating 2 phi minus 1 out of the total length here, which was 1 minus phi plus 2 phi minus 1, which should just be phi. Okay. So that's the recipe by which I eliminate the same relative amount at every stage of the iterations. If I just do the cross multiply and solve for phi here, what I'm going to get is a quadratic equation in phi. I solve that quadratic equation for phi, and it turns out that phi is 0.6 something or another, 0.618. This goes back to, I don't know, Pythagoras or the Greeks or something, which is where the whole golden section thing comes from. And this is also called the golden ratio. So what does this say? It says basically at every stage of this process, I'm eliminating about 32% of the length of the interval. And that's basically the best I can do unless I start using derivative information, which is what I'm going to do for the next method. Okay, so any questions about that? Okay, so and then in terms of where does this get us to, we keep narrowing down. Eventually, I'm going to be in some very, very small interval. I've sort of narrowed it down to like this, and I say, this one, this guy, and this guy are so close, I can just take the average of those two and report that as my answer, and that's exact enough for whatever purposes I'm interested in. I could choose that tolerance of how accurate I have to be just based on subject matter, how close I think I need to get. I could choose it based on machine epsilon. I know the computer's not going to be able to represent numbers accurately down, below some certain value. So we'll see sort of more about that in one of the later classes for this unit. Okay, so the next method we'll discuss is something called bisection. And the idea is we can actually, with bisection, do this search faster, but it comes at a price. And the price is that we need to use derivative information. Okay, so you notice in the golden section, I didn't say anything about derivatives. All I had to do was evaluate the function f at those various evaluation points. Okay, the idea of bisection is I'm actually going to use derivative information to give me a little bit more information, and the result is I'm going to be able to narrow down the interval by half every time, whereas here I could only narrow it down by approximately a third every time. So this bisection method is going to be faster. Okay, so what does bisection do? So basically I'm going to start with AT and BT, so assume I'm sort of in the middle of my iterative algorithm. I've gotten to the point where I've narrowed it down to between some AT and some BT, and now I have some XT, and I'm basically going to evaluate the derivative of f at each of these 3 points. Okay, so it turns out I'll already have it for these 2 points from the previous iteration, and I'll have to evaluate it at this point. And so then the question is, what does the derivative look like? Well, suppose the derivative is negative here, positive here, and positive here. Well, then I know that the minimum has to be in here. Okay, so I then choose this to be my new interval, and I'll take xt plus 1 to be here, and I'll evaluate the gradient at xt plus 1, and I'll continue on. And you'll notice I've eliminated half of the interval here. And if things look differently, if the derivative was negative here at xt, then I would have ruled this out as including the minimum, and I would have narrowed it down to this interval here. So I'm eliminating by halves instead of by thirds. Okay, so that's basically what this little recipe says here, is what are the derivatives and how do they compare to each other. Okay, and you can basically work out that for every decimal place of precision in your answer, it's going to take about 3 or 4 iterations to get that. So that gives you some idea of how fast the search is going to be. And this is called the bracketing method because we're basically trapping the minimum in an interval or bracket that gets progressively narrower as we move along. Okay, so any questions about that? Okay, so the next method is Newton-Rapson, also called Newton's method. You can think about Newton-Rapson as either a way of doing optimization or as a way of finding a root of a function, so where the function crosses 0. We're mainly going to be thinking about it in terms of optimization, but we're sort of going to frame the problem in terms of root finding as well here. Okay, so what's the idea of Newton's method? Okay, so for Newton's method, we need an additional derivative. So you can see we're sort of going from the first method that didn't require any derivatives to the second method that required a first derivative to when this method is now going to require two derivatives. So we're requiring that the function be sort of better and better behaved in terms of its differentiability. And again, we need that it be unimodal. Okay, and so we know that the minimum is going to arise at x star where f prime, where the gradient is equal to 0. Okay, so what are we going to try and do with Newton's method? Well, since we know that this is the case, we're basically going to work with the gradient function, f prime, and we're going to try and find a 0 of that function. We're going to try and find where that derivative function crosses 0. And the basic idea is to do a Taylor expansion. So let's suppose that this is f prime. Okay, so here's f prime of x. That corresponds to the optimization problem of minimizing the original f of x, and suppose that this is roughly, this is supposed to be exactly the gradient of that function there. Okay. So the minimum arises there, it's just the same point as the 0 is here. And now suppose that we're at x0. So the idea with Newton's method is we're going to take a Taylor approximation, a linear approximation to the function here. So we're basically drawing a tangent line here and saying, roughly speaking, in the neighborhood of x0, my f prime function looks like this straight line. Okay? Well, the nice thing about that is it's easy to find the 0 crossing point of the straight line. The straight line is an approximation to the function of interest. So we're going to find the 0 point where f prime crosses 0, and then that's going to be our next point, x1. Okay, so that's going to be x1. Now I'm going to continue the process of doing a Taylor approximation and finding the tangent line here. I'm going to follow that down to 0, and I'm going to keep doing that. I'm going to walk my way towards the 0 here, which amounts to basically walking my way down in the optimization problem as well. So if I actually write out the Taylor approximation for this problem, then I get that f prime of x is approximately equal to this. And I'm going to set this to be 0, and I'm going to solve for x. And when I solve for x, that's going to give me my x1, and that's going to be a function of x0, f prime of x0, and f double prime of x0. So this is my new x1. That tells me what x1 is, and then I just march my way along and continue along. So the general updates are, would just be written as xt is equal to xt plus 1 is xt minus the ratio of these derivatives here. Okay, so with Newton's method, we have a lot of power and this converges really quickly, but things can actually go awry in a number of different situations, and we'll talk about that next. But if things are really well behaved, if the gradient is twice continuously differentiable, if we have convexity and if there is a root of this function, then we can prove that it converges from any starting point. Okay, so I think these conditions are maybe they're helpful to to know about in terms of thinking about sort of these methods from a sort of theoretical perspective. But in a lot of cases, we're trying to do optimization where the function isn't this well behaved, and so we need to think about what can go wrong. I will mention, because this comes up a little bit later when we start talking about multivariate methods, is that if it were expensive, for example, computationally to calculate the gradient here, we could instead of taking the tangent line here, what we could do is we could basically take a secant. So we could take a point here and a point here, and we can approximate with a secant that joins those 2 points instead of trying to find the tangent line to f prime of x. So that might, in some cases, reduce computation. So that's basically finding a numerical estimate of this second derivative. Okay, so let's think about how Newton's method can go wrong. So I think what would be helpful here is to just pause for a minute and have people sort of try and think about drawing out functions and think about what would happen for different kinds of functions. So let's go back to our original function f, and I sort of drew it like this, and I said, okay, the result of that is I get a gradient function that looks like this, and then I'm going to draw tangent lines, and I'm going to march my way to get to the 0. So what I'd like you to do is take a minute and see if you start drawing things that don't look as nice, sort of that don't look as nice and quadratic as this. Can you get a sense for what can go wrong with Newton's method and how it might not actually find the minimum? So play around with just sort of trying to sketch out sort of what happens as you change the function and make it not as well behaved as this, and try and get a sense for what would happen as you what the gradient would look like and what would happen as you try and follow along the tangent lines. And then we'll reconvene in a minute and see pick up from there. Okay, so the illustration I gave before was what if f prime, I sort of had f prime looking like this, and I said, okay, we draw tangents, and it seems like we're going to zero in on the right answer. So how could I change this picture such that things wouldn't behave that well? Yeah.
You have an absolute value to take minimum as a corner.
Okay. So yeah, I guess that would probably, we're going to run afoul of the requirements for this, which is that we have enough derivatives. So this is not going to have enough derivatives for us to be able to apply Newton's method.
You have a cusp.
So what the cusp is sort of a little thing like that, or what is a cusp? What's a cusp?
It's like
Okay, I think we're still not going to have a second derivative there. So let's keep things sort of smooth, although it's useful to think about what happens when things are not smooth. What else could happen here?
We will assume there is only one minimum.
Yes, I'm assuming. Well, okay. So keep going with what were you thinking there?
If you have multiple, then there's a possibility you will jump around to almost in there.
Okay, so that's one thing to think about is sort of are we going to go in the right direction? So what happens if we've got a function that looks like that? So what's going to determine whether or not we end up here versus here? Okay, where I start? So presumably if I started here, I would actually converge down here. If I started here, I would converge down here. Anybody seeing what else could happen here? Okay, there's nothing that says that I have to go downhill here because I'm just trying to find a 0. So if I actually start somewhere like here, we could actually see, and we'll probably maybe play around with this a little bit at the start of class on Monday, we could actually see that the method says to follow the tangent line uphill instead of downhill. Okay? And so we might end up converging to here. So if we had this situation, we could end up converging to here, we could end up converging to here, we could end up converging to here. And it all sort of depends on where we start and what the various values of the gradients and the second derivatives are as to sort of what direction we go off in. We have another minute left, so let's play around a little bit with the idea of what would cause us to, suppose we've got a situation like this. Anybody have any thoughts of what would cause us, depending on if I'm placing a starting value somewhere between here and here, what would determine whether or not I converge to the minimum versus the maximum? Yeah, so it's got to have something to do with the second derivative. So it's sort of the same sort of intuitive, like, well, what goes on here? Well, there's some inflection point here where we sort of start to turn over. And if we go back to our recipe for Newton's method, what does it say? Well, it says we're going to go to the left, negative, if both of these are positive, right? So if we're down here, then the gradient is indeed positive and the second derivative is positive, right? But if we're up here, the gradient is still positive, but we've gone past the inflection point, so the second derivative is actually only going to be negative. Okay? The gradient is starting to decrease instead of increasing. And so in that case, we're going to have minus, positive, minus. This is going to be a plus, and we're going to move to the right instead of going to the left. So if we're past the inflection point, we're going to go this way. If we're on this side of the inflection point, we're going to go that way. All right, so let's quit there. We will see another example of how Newton's method can go wrong when we come back on Monday.